Okay, so I'll try to keep the presentation a bit simple, but it might be a bit too simple, but I'd rather like have people understand. So I'm gonna start with some background on what a blockchain is, how it works. It's gonna be briefer than like a proper presentation. If something's not clear, that's perfectly normal, but I just need need you guys to have a general idea just to follow later because the language is now it's just a programming language. But if you really get why it's so useful to have one like this, well, there's no point, you know. So let's have some background. It's gonna be more about simple questions like what is a blockchain? You probably, if you came to the Ethereum presentation, we probably already know this because we covered a bit the topic, but briefly, a blockchain is a globally shared transaction database. What does this mean? It's that the blockchain is a database, so that's the keyword here, I guess. It's transactional because every single change you do to this database is done through what we call transactions. So every time you want to interact, you do a transaction. It doesn't need to be an economic transaction. It could just be a change of something. You know, if you're changing a value, even if it's not an economic value, but maybe I have a ticket or not, that still counts as a transaction. And it's globally shared. So globally shared means that it's usually public and it's available to everyone to check it. So you can always verify the content inside the blockchain. Now, what makes a blockchain secure is the consensus algorithm, which I'm not going to cover in today's presentation because otherwise this would be like a 2 hours long presentation. But just keep in mind, what you know is that like you have a bunch of computers connected together and they all have a copy of the state of the blockchain and they all communicate together through this consensus algorithm to be able to agree on a global state which we know is secure in the sense it cannot be manipulated by a malicious actor. You can always assume that the blockchain is always saying the truth. Okay, so those are the nice properties that make it interesting to develop on a blockchain. Now, yeah, it's just a database if you really want to simplify things. But since we're here at Lozak, I'm also going to say it also works in the case of Ethereum as a decentralized server. So it's kind of an API. In the same way you would have a normal server in a Web2 environment. So, an API that you can call and it gives you some responses. You can also do the same thing with Ethereum, which kind of replaces the API's calls to a secret server with calls to the blockchain, RPC calls to the blockchain that kind of behave in the same way. So if you want to know, for example, if you have a ticket or not for an event, instead of calling a private server that is hosted somewhere in a place, maybe AWS or whatever, you can just query the blockchain and you can verify that this person has a ticket or not. I'm talking about tickets a lot because the example we're going to do today is about ticketing. I'm going to do some fake Balélec ticketing system since Balélec is around the corner and I'm very hyped. So let's continue. So why Ethereum? Why I'm talking about Ethereum and not Bitcoin? Well, the reason is very simple. Well, Ethereum pioneers smart contracts. And when I'm talking about smart contracts, I'm talking about pieces of code that we write in Solidity. And well, of course, if you came to this crash course, you know we're going to talk a lot about Solidity. It's a blockchain with a good level of decentralization and security, but not the cheapest. We can also discuss this offline if you want, or you can ask the BSA members. I'm going to tell you why. But we can say that it's not cheap because it's very secure. And it was created by Vitalik Buterin when he had this intuition of making Bitcoin more extensible. Because before, well, Bitcoin had some programming capabilities, but you could not really write smart contracts on top of it, which means Bitcoin in its purest form can only do very simple stuff. You can only send money from person A to person B and stuff like this, but you cannot really create custom conditions easily. So you cannot say only if this condition is met, give some money, for example, to this person, or you cannot create lending systems. You cannot exchange multiple currencies, which is something that is totally possible in Ethereum. And this is why it was the very first one to adopt this. And this is why Solidity is so important right now, because it's the most widely used language. And we're also going to see why. So I struggle a bit. Sometimes I have the impression that you're raising your hand. If you have questions, please don't hesitate to let me know. Maybe also stop me because I cannot really see it. So yeah. So I've been talking already about Web 2 and Web 3. I hate myself, but we have a lot of jargon in crypto and blockchain in general. So when I'm talking about Web 2, what does that mean? When I'm talking about Web 3, what does that mean? Well, Web 2 is more blockchain. It's more like servers in the classical sense. So every time you're interacting with a service, maybe you're using Google or you're doing something else, you're using Facebook, whatever. As long as you're on the internet, I would say you're always using some private servers. You're interacting with them, and they provide you a service, but you don't really know what's going on. You just request that thing to happen, and they give you back an answer, and then the browser shows you the answer very nicely. And so these are some implications since those servers they're not public, they don't really communicate with each other. So each one of them needs to have a different account for each service that you want to use. I mean, this got much better with years now that Google is sort of unifying everything, so you cannot log in Google and access everything. But before, you still had to make a different account for every single service. So it was Meta, Instagram, Facebook, Google. Every single one of those was a separate account, and this was messy. Now we are under the impression that everything is the same because you're logging with Google, but this doesn't change the fact that you're still like have separate servers that don't really know each other, that they're storing the same information multiple times. And in Web3, the approach, so in blockchain, is that you just have a wallet and you can use it to access your blockchain account. So what is a wallet really? I guess you could say it's a collection of two things. It's a private key and a public key that we also call an address. We're going to see, I mean, let's just say public key and addresses are the same thing. So you have a private key, which you use to sign transactions. So to modify the state of the blockchain, if you have to move your fund somewhere, you always sign a transaction with your private key, which of course you keep private. So that's basically your password. And then on the other side, you also have an address, so a public key that you can use to give it to people. And with that one, people can send you money. You can check how much money do people have and things like this. So this is a kind of different approach because the key difference here is everyone is storing all the data in the same place, which is the blockchain. So since everyone is storing everything in the same place, you can just access the data and modify the data with the same private key and address. And this kind of concept, I really like it because it simplifies login by a lot and it makes it more secure because it's cryptography by default. If you are in computer science, and I guess most of you are, you know about asymmetric cryptography and how powerful it is. So this is a nicer approach, and it's something I honestly would like to see in general because we get so many of those accounts and you don't really know every time what is happening with your data and stuff, while here you fully own everything. So as I said before, in a Web2 approach, data are stored in the private servers. So you have to trust them. You know what they're doing with your data, and in general, you don't really know what's going on, And if at some point something stops working, it's lost. It's just lost forever. That piece of information is lost. Like for example, like I remember when I was a child, I used to play a video game which I liked a lot, which was called Paladins. It was a sort of Overwatch clone and was very popular at the time. Maybe some of you also tried it. And now this game is really, really going bad. It's not updated anymore and stuff, or not as it was before. And I'm honestly scared I will lose all my progresses and my ability to play just because everything is in their servers in the end. Like if they shut down the servers, the game is it's not there anymore. And this makes me sad. And this is a paradigm that is significantly different in Web3, where everything is on the blockchain. So in theory, you could also be able to store things and things functioning without relying on people hosting the server. Because in the end, it's just these networks of computer that is keeping your data alive, and they all have a copy of the whole thing. So the whole history of the blockchain is stored when one computer is running a blockchain node, what we call a blockchain node. Now, I think I've already said a lot of stuff. Any questions so far? Cool. Okay. If I didn't see any hands, please let me know if I missed one. So yeah, maybe something I wanted to show you, which is I think it's really cool, is that the cool paradigm of blockchain allows you, as I was said, to see what's going on. So don't trust, we can just verify ourselves. So I'm gonna go to this website. It's called Etherscan. If you wanna check it at the same time, it's just etherscan.io if you wanna check, and we can have some fun here. This allows you to see the whole state of the blockchain. So as we speak, we can see all the blocks being produced. Let me see if I can show the blocks. Yeah, latest blocks. So you can see on Ethereum, for example, every 12 seconds, more or less, you have a block produced. And this block contains a bunch of transactions. So you can see here, for example, this block contained 142 transactions. And you can inspect every single transaction. You have a kind of an idea what's going on. For example, you can see this was a transfer, this was a claim or whatever we claimed. This was a swap, so we exchanged cryptocurrencies. You can make arbitrary programs doing stuff on the blockchain, which I think it's a nice property, and you can see everything as it happens live. So every single person here, as I said, here we can see this transaction was sent from a certain address. So again, the address is the public key. The person that is sending the transaction, we can see here who has done this by using its private key to sign. And we can see exactly what he has done. So he has done some manipulations with USDT and Ether. It doesn't matter. Just the point I'm trying to make is you can see this stuff happening in real time, and by this approach, you have transparency, which is very cool. And maybe something else I wanted to mention, but we'll get back to this later, is that every transaction, so if I pick a random one here, has a cost. Why does it have a cost? Well, because the blockchain, to be secure, it asks many people to store redundant data and have these computers be running all the time. And so we need to somehow pay for the storage and their costs. And also for the security we're getting by doing this instead of a centralized server. So this is why we have to pay transaction fees. And we'll get back to this later. But I guess this was good enough as an example of what you can do with a blockchain. And you can literally see every single piece of information is here publicly available. Like, let's get back to the presentation. So why I think Ethereum is cool, it's because it is blockchain as a service. Okay, so this is why we're talking about Ethereum and Solidity specifically, and not, for example, Bitcoin, because Bitcoin has its own very limited scripting language, but you cannot do a lot of things with it. There are three main reasons to build something with Solidity, so on Ethereum, or we'll see other compatible blockchains. The main reason is security, because of course, if you're using a blockchain, it's because you need some properties that a normal server cannot offer. So if you just want to be sure that the data are gonna be there all the time, no matter what, they're gonna be only modified according to conditions that you specified in your Solidity code. Well, the blockchain is the right place because you could do something similar on a centralized server. You could expose APIs for everyone to modify things and change data. But in the end, you don't really know what's going on behind the scenes. You haven't seen the code. This is another thing that is important about blockchain. Everything is publicly available. So maybe I think this is worth showing. For example, here, if I go to any transaction, this is a function call from a Solidity contract. We'll see this later. And if you look at this, what you're going to notice is that we interacted with some contract, and here we can always see what happened exactly because, you can just check the contract. Okay, so this is not a contract. This was a mistake because it was just a transfer. Yeah, let's take this one, for example, or let's see if I can find a swap. Yeah, great. So this was an exchange of cryptocurrencies. And if you go here, you can just see interacted with the contract. And you can see the Solidity code of the contract. So you don't have to trust the server. This stuff is running according to the law, and the law is the contract. Okay, so here you can check the code and you can see which function was called and what did exactly. So it's not, sometimes when you're using centralized service, you have errors, you have error code for whatever, like 561. and you have no clue, because okay, the error code tells you some, some intuition, gives you some intuition on like what could have gone wrong, but you cannot really debug things yourself. And one thing I find it funny as a computer scientist is that when you're on the blockchain, you can really, like, if something goes wrong, you can really tell what went wrong. And if the problem is not on your side, but maybe like it's just the devs that did the thing that were incompetent and did something wrong, you can tell and you can shame them publicly, which is funny. Because yeah, like everything needs to be transparent, and I think it's a very nice property because everybody tries their best to do things as basically the best they can. And yeah, and another cool thing is, well, if you really like what someone did, usually you can just copy its Solidity code and you can improve it, and it's just fine. It's not, there's no corporate secret, there's no private code, everything is transparent basically. Okay. All good so far? Nice. So let's get back to the slideshow. So the first property is security. I think I've said enough about this. It's transparent by default. It's just we have security guarantees given by the fact that we can see what's going on all the time. We have convenience in the sense that this is a more specific one for Ethereum and for like smart contracts enabled blockchains. It's very nice to have Ethereum and not Bitcoin, for example, because on Bitcoin, if you wanted to do stuff, I mean, if you wanted before Ethereum, what you had to do if you wanted to like make a blockchain-based product is that you had to like build your own blockchain from scratch, which means you had to handle consensus and a bunch of like very complicated networking parallel stuff, which you don't have to do anymore, because on Ethereum you just deploy your contract. So it's a bit like installing the contract on the blockchain, and then it's there forever. That's very nice, and it's just working, and you don't have to think about, okay, but how are those computers like gonna communicate with each other to make sure the information is true or not. It's just easier. Just focus on the Solidity code, which we're gonna see like what we're gonna work on. And Solidity is gonna be 30 lines of code. It's gonna be very dense in explanations. But in the end, you're going to see with like 30 lines of code, you can get a perfectly functional ticket selling system, very simple one, but it works and it's secure by default. So this is very convenient. And then the last property that I really like is composability, which is something that you kind of have in Web2, I would say, but this is like just brought to another level by Web3. And what composability really means is that you can just build applications one on top of each other. And it's not like just taking the API of one thing and doing another thing, a bit like maybe we see with a lot of AI products right now, where you can just take the OpenAI API and you can just integrate it. This is at a much deeper level. Everything on the blockchain is composable by default. Everything in the blockchain can be expanded by other people. So if you have a very nice product that you like and you want to add some features on top of it, most of the times you can just build a contract on top, and this just works, and it's so nice. So to discuss about Ethereum matters, of course, we need to, as I said, we need to pay for transactions. So transaction fees are paid in Ether. Ether is the native currency for Ethereum. We're just going to cover this for now, but keep in mind that if you want to, Ethereum can support any type of currency. So in Solidity, we can handle any type of currency. For now, we're just going to handle Ether, to keep it simple for the demo and for the workshop. And the amount you pay in the transaction I've shown you before depends on the complexity of the operation and the state of the network. So what do I mean by that? It depends on mainly two factors. The first one is how complex the operation is. So if you're doing a for loops on over 100 items, the operation is going to be cheaper than an operation that does a for loop on 1,000 items or 1 million items, of course. And this has some deep impacts on how we conceive code in Solidity. A lot of things that would make sense in, for example, Java, don't in Solidity, just because you need to be cheap. You need to have cheap execution all the time, because if someone finds an optimization for what we call gas, so gas is like what you spend to execute transactions, so Ether in the end. If you find a better algorithm to do something, you're gonna have a competing product that is cheaper. So people are gonna go into the other product because it's cheaper. So it's really important to like consider how complex your code is. And actually, fun fact, almost everything in blockchain is done in O1. Like you rarely see for loops in Solidity code, and that's exactly for this reason. Everything has to be as efficient as possible. Or if you see for loops, they're always like bounded to like a constant number of elements, so it kind of stays to O1. And yeah, so this is the first thing that impacts the price, so the complexity of the operation. And the other thing that impacts the price is the state of the network. So maybe let's go back to Etherscan, and you can see here. Let me see if I can find it. You can see here this is the kind of the state of the network. So this is how much you're paying for transactions. You can see it's 10 Gwei. Gwei is just as an amount of Ether. It's like 0.000001 Ether is a Gwei. And what is really interesting here is that you can see that like operations have a fixed cost depending on their complexity, but this cost is multiplied by the state of the network. So this is like a coefficient you use to multiply to the complexity of the operation to obtain well, the actual price, because you know Ethereum can do only a limited amount of transactions while keeping its security properties, and this implies that you have we have to do some compromises. So this is like governed by supply and demand. When something when there's too much demand for transactions, so too many people want to do transactions, we just make them more expensive, so that some people just give up, and only people that really need that thing make it end up sending the actual transaction. This is not the most democratic thing in the world. We know Ethereum is not cheap for this very reason. As you can see, a swap in these conditions, which are extremely low gas conditions, it's $10. So imagine just if you want to exchange a cryptocurrency, maybe you do it by mistake, you're spending $10. This is not cheap. This is not inclusive. This is not the best, but we have solutions for this. And actually, I think we're going to cover this in the next slides. And it's very important to cover this because let me see if we get it there soon. Okay. We're not there soon, so I'm gonna say it now. Basically, what the solution for like how expensive these transactions are is that we made other blockchains on top of Ethereum, which use Solidity as well, so they're compatible. You don't need to do the work again. But the advantage is you just get the transaction are cheaper through some technological compromise that we're not gonna discuss here. But you can, for example, if we take another Solidity compatible blockchain, it could be Arbitrum, and I go in their blockchain explorer, you can see here transactions are much cheaper. Let's pick one, a random one. So let's pick a block or a transaction. You can see here a transaction is like costs very low. I can't even find the cost, but yeah, okay, here, transaction fee. This was less than a cent. This was 0.3 cents. And the advantage here, the key thing you need to remember is those blockchains, they also contain significant value. So they have users, they have people willing to use them, and they're all compatible with Solidity. So you just do the things and you once, and you can deploy everywhere. So now let's get back to the slides. Is everything clear so far? Good. Now, what you can see here is 3 examples of like 3 of the most used decentralized apps on Ethereum. So here you have Uniswap, which is a website that you can use to, well, exchange tokens. So here you can go and you can just exchange any cryptocurrency with each other, and you just get this on the blockchain. This is not Binance. This is just you owning your funds for real. We could spend hours and hours talking about this, but like this is like you're actually own your assets here, and you're not doing any compromise by trusting a third party to trade assets for you. Okay, this is the key takeaway, and this is built on the blockchain through smart contracts in Solidity. And we have similar applications. Aave is for lending money and borrowing against it. And Maker offers a stablecoin. So if you don't know what a stablecoin is, it is a token, so a cryptocurrency that holds that basically has a value that is pegged, so linked to the dollar. So it's guarantees that it's always worth $1 as long as the smart contract functions correctly. So if you do a mistake here, you might actually do some real damage. And why am I showing you this? Well, the key takeaway here is that those applications were built using Solidity. They're very powerful. They enable incredible financial applications. And what is really interesting is that they have significant value, and you can extract some of this value. Like, for example, here, this dashboard is called DeFi Llama. It's one of the best for finance in blockchain, especially in Ethereum. You can see, let's just have a look, like the biggest blockchain by TVL, so the amount of money inside the blockchain, that could be under any form of token or anything literally. There's like 51 billions only on Ethereum. So by learning Solidity, you're addressing this market. So you can already reach 50 billions, and you have here a bunch of other smaller blockchains which are not as big as Ethereum, but the key thing is they are cheaper, and most of them are all compatible with Solidity. So you can just write the code once and you can access a bunch of different markets. For example, Ethereum, okay, we got it, it's a big one. But then we have Tron, which is more used in like countries like South Africa, I think, and also I would say Africa in general, and like Nigeria, and this for whatever reason, for historical reason, this blockchain is very used in African countries. This one is very used in the Chinese community, so this is actually operated by Binance, but it doesn't really matter. But this one is also compatible with Solidity. That's the point. Arbitrum also compatible with Solidity. Blast also compatible. Base also compatible. They're even trying to make Bitcoin compatible with Solidity. So what I'm trying to say is there is a very big market that you can address, and you can capture a lot of value from it because you just deploy on the blockchain and you capture all this user base. All these applications here, like all the biggest ones, are all written in Solidity. Yes, I wanted to show you, like, for example, Aave is one of the biggest ones. There's like 10 billions in it. Uniswap, 5 billions. And Maker, let's see, 7 billions inside Maker. So you can access a lot of value from this by constructing real applications, and I find it's really interesting. And yeah, I guess we're done with the background part. So hopefully now you have some you have a better understanding of why Solidity is so cool. And yeah, any questions so far? Okay. So now we're gonna move to the actual language. I'm not gonna do the thing where I just say, hey, this is how you declare a variable, this is how you do stuff. I guess if you're here at EPFL, you have a somewhat decent level of programming to be able to follow, but I'm gonna do a very basic example with you guys, and I hope this is gonna work because I'm just gonna explain all the details, and I'm gonna focus on like the key parts. So before diving into the code, according to their definition, Solidity is a statically typed curly braces programming language designed for development of smart contracts run on Ethereum. In simple terms, and from my experience, it feels like C with some sprinkles of Python. It's as verbose as Java, unfortunately. Has some very specific issues of its own. We can discuss this later if you want, but there are some really funny problems that you have only on Ethereum or in general only on Solidity. And it is a very young ecosystem, so some things that you would take for granted on like other languages, you don't have it. For example, if you have had to write some Java code, I'm sure you've used IntelliJ and you were surprised by how good it is at auto-completion, correcting errors, in general, providing a smooth user experience, integrating tests and everything. This is not the case on Solidity. We don't have a good IDE yet, mainly because there's not enough funding for it, but it's getting better and better by the day. So hopefully at some point we will be able to like develop Solidity with ease. But for now, I would say this is also why this is such a valuable language to learn, because if you learn to do proper Solidity, the average salary is way higher compared to like Java-based job, for example, just because it's a very niche skill set that you need to master, and it's harder to learn than things where you just have everything on a basically served on a plate. So I've been shitting about it, but yes, why should I use it then? Why can't we just use normal programming languages to do this stuff? Why do we need Solidity in the first place? This is probably the question you're asking yourselves. And the answer is because of the Ethereum virtual machine. So basically what is happening is your Solidity code is not compiled to normal assembly, nor any computer compatible bytecode like Java bytecode, for example. When you are building in Solidity, you're compiling to Ethereum opcodes, so they have their own kind of assembly or low-level language, if you will. And the peculiar thing about this very specific virtual machine is that it's a stack-based virtual machine, so they wanted to try something a bit different. But by doing this is one of the main reasons, but of course not the only one. We made just the compilation process incompatible with a bunch of cool things we have so far. Like, for example, we're trying to build, if you're familiar with it, the analogous of LLVM for Ethereum opcodes right now, because we don't have it. We cannot use normal machines because they are register based. So if you've taken a computer architecture class, you know for sure that like machines are mostly based on registers, and like the Ethereum virtual machine does not do that. It doesn't have the concept of registers. Everything is a stack. So it's different. It's different, and we lost a bunch of optimizations because of this. The other cool thing about the Ethereum virtual machine is that it's widely adopted. So all the blockchains I've showed you so far, like the ones that were compatible with Solidity, they were because they were EVM compatible, so Ethereum virtual machine compatible, which means they all run the same virtual machine because they took the job done by Ethereum and they said, okay, this works, this is nice. We just have this compatibility and we obtain a bunch of developers that don't have to learn a new language just to write on our own blockchain, which is very nice. And this is why Solidity was so popular, in the end. It was also first mover advantage, Ethereum was the first one to implement this. People were like, okay, the design works. The design seems to be sound enough to work. It has some limitations, of course, as I said, but it was just good enough, and people kept it. So this is why we have so many EVM compatible blockchain, and this is why in the blockchain market, I think Solidity has 80% of the share. So it's the most used programming language by far. So yeah, write Solidity once and you can deploy everywhere. I guess I've seen this too many times. And another cool thing is that since it's the biggest one, it's extremely well documented. And in general, like the tooling is the one with the most mature tooling, which does not mean the tooling is good. It means it's better than the other competitors so far. So to give you an idea, for example, of how well documented this thing is, and maybe you're curious about this infamous stack-based virtual machine, there's a cool website that you can go to, which is called EVM Codes. And here you can check all the assembly codes of Ethereum. And if you look at this thing, honestly, I can confidently say this is the best assembly documentation I've ever seen so far. Like you can even go here, you can simulate things, you can see how the opcode behaves. Like honestly, if you show me something built so nicely for another processor or assembly language, please let me know. But what I'm trying to say is people really put a lot of love and effort into this kind of documentation, and in general in the Ethereum products, as young as they may be. So moving on. So let's see, where are we at? And so another key takeaway that you need to have and to keep with you is time complexity becomes cost complexity. So as I said before, in programming in general, you care about time complexity. You want things to be efficient because efficiency translates into less energetic consumption, and in general, yeah, that's it. But here it's slightly different. On Ethereum, we're not doing hard computations. We're just making them secure. So most of the operations, most of the times are just literally like increasing by one the balance of someone if we received something, for example. We're not doing complex operations. So what we're really optimizing for is not the time it's gonna take, because anyway, we can only produce 12 blocks, 12 no, one block every 12 seconds on Ethereum, but it can be made faster, but never as fast as an actual computer, because here we're looking for security. And so what we're trying to do is just trying to make it as cheap as possible to obtain a secure execution. So in the end, it doesn't change much. It's the same thing, you know. We're just trying to reduce, you know, the ON complexity. We want to bound as much as possible the execution, but not because this takes time and so energy, but because this just costs money, because every opcode I showed before, every single assembly instruction has its own cost, that it's very well defined depending on what we're doing. So yeah, I guess that's it. I have some bonus slides if there are questions, and I think I even have a couple of minutes maybe to ask questions. So before we dive into the coding session, please let me know if there are some questions that are more on the theoretical side. All good so far? Can you hear me good? Can someone from BSA just say yes if you're hearing me good? Okay, nice.
Yeah, you can on coding? Yeah.
Yeah.
Okay, let's start coding.
Okay, so to code, cool thing is we can code together. There's no installation requirements. You can just go to this website. I'm gonna give you some time to do it if you want to follow along. I'll try to be as low as possible. The website is called remix.ethereum. 1 second. The website is called remix.ethereum.org. I'm gonna give you a minute to set up your laptops if you need to. Can someone give me a sign when everyone is done?
Yeah, we're good.
Okay, cool. So if you did everything correctly, you should have a page that looks kind of like this. And what we're gonna do is that we're just gonna make a new workspace here. So if you go here, you can just go to workspaces and you can create a new one, and you can just call it something. We can just use the default template, so basic one, and you can just call it whatever you want, honestly. So let's say the Zach BSA, and we'll just say okay, and okay, special characters are not allowed. Let's do this again. Okay, I think I know what the problem is. Okay, we did it. And if you took the default template, you have a bunch of stuff we don't need, so we can just safely delete basically everything. I'm doing this with you so that it's easier to follow along. And then we can just make a new file. So there's a button here, which allows you to make a new file. And if you just make it, as I said before, we're gonna make some sort of like tickets for Balélec, which I find it really funny. And you're gonna see how simple it is. So we go here and we just give it whatever name you want, tickets. And the important thing is that it has to be a .sol file, because .sol is the extension for Solidity. And there you go. Already here, you can see that we have some warnings here. So just to give you a brief introduction on the IDE, there are just two things you need to know. This is to access the compiler and see errors. This is to actually deploy and test the code. So if we move to the compiler, you can see we don't really have errors. We have warnings. Okay, so these warnings are quite important, so I'm gonna go over those. The first one, it's telling you, hey, you forgot to put a license identifier. So why in the world do we need to put a license in code? Why is it so important to the point that like we have the compiler complaining about this? Like in Java, you don't have this. In Python, you don't have this. And whether you can use MIT or literally anything will do the job, like even unlicensed. The reason why it's so important to have a license, it's because on the blockchain, everything is open source by default, which means if someone copies your code, you have no way to prevent it, you know? Sometimes this can be frustrating. So at the beginning, it was like people were very open to open source, but at some point project would just be stealing their code and do no effort whatsoever and just, you know, deploy with different branding and focus on business development. And this was frustrating. So people started using commercial licenses to protect their product, which means the product is still public. It's not open source anymore. You can verify the code, you can audit it. But if you end up doing, you know, copy pasting the code without the authorization of the user or of the creator, for example, well, you could get sued or stuff like this. This is something that could happen. And then the other thing that Solidity is requiring us to do is pick a version, and this is more for security reasons because again, you know, on blockchain, the compiler version could change the behavior in unexpected ways, and so if you're not explicit about the version, we could have problems. You know, in Python, if you're executing code with a different compiler version, worst thing that can happen is that the compiler, the interpreter doesn't run. It just raises an error or it says, hey, this is not working, or maybe some warnings. But here, if you have some unexpected behavior, this is a problem. So we need to address this. So we're just gonna pick the latest version of Solidity that we have so far, which is this one. And as you can see that now we have no warnings and we can finally start writing a contract. So the first, yes, questions? No, okay.
Yeah, there's a question.
Who
Okay.
issues the licenses?
This is something you usually need to either you use a commonly known license like MIT if it's open source, so it's easy, you don't really care. But in some cases, and this is sort of a gray zone from a legal point of view. The usual approach is that you need to have a company, usually the company that developed the product, which does some legal paperwork to have a proper license, and then you just have basically something that is good enough to protect you. But of course, you cannot prevent people from copying your code. Just if you know, if someone copies your code and you had a license, it's already good enough to like scare users because they would be like, okay, this guy just broke the law, so I would not be willing to use like unlawful code, for example. But again, this is more like a subject to discussion. Some people are like, yeah, everything should be open source by default. This is nonsense. Some people are like, do whatever you want, you know, the license doesn't make any sense anyway, it's not really protecting the code. But I would say it's every time it was used in a more restrictive way, it worked fine, in the sense I could still read the code, I could still learn things from it, I could still make better versions, but I cannot just steal the work of someone else and say, hey, you know, I'm making a company, you know. It's like, yeah, but it's a very rare situation. Most of the times it's just fully open source by default. Like, to give you an example, I think the only contracts that are like licensed are for the biggest ones, really, like Uniswap, Aave, those that like go to a point where like they spend millions or even billions in development and research, and then they don't want to see their work stolen. But again, most of the times it is not even necessary. So does that fully answer your question? So yeah, it's just the company that if they want to, they need to use a license and they need to do the legal work for it.
Okay, thanks.
Cool. So why now what do we have to do is we create a contract. So this is easy, we just say contract. If you are familiar with Java, this looks a lot like classes, but they're fundamentally different. Just in general, like for example, You could do inheritance with this stuff. So you could do super classes, super contracts, subcontracts, but this is not always the best. It depends. There's a lot of debate. So let's just focus on what we're going to do here. But keep in mind, it sort of looks like a class. If that can help you. If you have no clue, it doesn't matter. It's really not important. So we create a contract, and we call it, for example, Balélec ticket seller. And we just open the brackets and see here the compiler is working. It's auto compiling anyways, so it should give you just a tick, a green tick. And if you manage to do this so far, you have an empty functional contract, which is really nice. And here we're going to do a couple of things. So we need to store two very important pieces of information. Again, what we're trying to do is that we're trying to sell tickets for Balélec in an imaginary world where Web3 is not just about cryptos, but it's also about, I mean, in the future, I mean, what I hope to be the future. So it's also about like real world usage. So what we do here is that we need two pieces of information. One, which is how much do people have to pay for the ticket? And the other piece of information we need is who has the ticket and who doesn't. So for the first one, I mean, no one is going to be surprised here, but hey, we need the variable. So we can just make a variable, we call it price, and we can say, hey, the price is equal to 30. What this 30 means really, I mean, it's a number. The Solidity doesn't know it's the price of something. We're going to see how we do this later. But the key part here is, the key part here is, yeah, I don't know what I was going to say, but this is just, oh yeah, sorry. So this is a price, but price in what, we said Ether, we pay things in Ether, but like, what is 30? Is it 30 Ether? Because if it's 30 Ether, for example, this would be quite an expensive Balélec ticket, So no, this is Ether, 1 Ether, and Solidity is 10 to the power 18 way. So way is the smallest unit you can have for an Ether, and this is done to have like smaller prices. And so yeah, here for example, we're making the price of the ticket 30 way, just because we are using the smallest unit, but we could also do like one with a bunch of zeros to have 1 Ether. But here let's just keep it simple. Let's make things be paid in way. And here we need a couple of things. This is not Python, this is statically typed. So we need the type for the variable. So what we're gonna do here is that we make this uint 256. Okay, so here there's a couple of things going on. This is an unsigned integer. So an integer that can only be positive. And we use 256 bits to store this value. You could argue 256 bits, it's a bit overkill to handle just a value that could be 30. But in general, with larger prices, this is usually the standard. So it's better to have this amount of space to handle like amounts precisely. Because of course, yeah, we like, for those that are curious, we don't even have like floating points, so you need to use fixed points. So having this many bits is very nice for precision. But yeah, we're just gonna keep 256 here for simplicity, since it's kind of the default on Ethereum. And then here we can also add one more thing that is very important, and we can make this public. By making this public,
There is a question.
Yes.
I have a question.
Is
Yes.
there an automatic library to like set the units of the price or something, or you have to stick to what is set?
The question is like to set the units. Oh, you mean like instead of writing this amounts, is there a library to do this thing easier?
Yeah, exactly.
Okay. Yeah, it's built in. I just didn't want to overcomplicate things. But for example, if you want to 10 to the power 18, you can either write it like this, and this is 1 Ether, and it works. Or you can even build, you can even say 1 Ether. It also works. This means 1 to the power 18.
Okay, and you can do like €1 or like, can you use any currency, or how do you
Yes.
convert it?
You can handle any currency. We're sticking to Ether for simplicity. Feel free to DM me if you want a full answer. But yeah, it's a whole Pandora box. But yes, you can handle any kind of currency. So of course, Ether, as you might have guessed, is not an ideal currency for paying for things because it's volatile. So well, one day your Balélec ticket is worth $100, and the day after it's worth 20 just because you bought this with Ether. So yes, I agree with you. This is not an ideal currency. You can use any kind of currency available in Ethereum, so also dollars through stablecoins. But it's a different process, and I'm gonna stick to Ether just for simplicity. Okay. But feel free to ask questions. I mean, the BSA members here are very knowledgeable about this, or we can also discuss this in we can chat about this like at any time I'm on campus, or we can also like chat in DM. So yeah, I had to do some compromises to make this thing simple and simple enough for everyone to be able to follow, even though it's like only a 45 crash course, basically 45 minutes crash course.
We have another question.
Yeah, I
Yes.
just wanted to clarify the ether suffix. So like if you put the way suffix, that's just like ×1. So it's just a multiplier thing, or how is it?
I couldn't hear the question. I'm sorry. Can you
Like
say it
when,
again?
when you add ether after the number, is that literally just a multiplier, or does it
Yeah,
sometimes
it's literally just a multiplier.
so
yeah,
if you add
that's
way, it doesn't change anything.
Yes, it doesn't change anything.
Thanks.
Okay, cool. So yeah, this is just writing this or writing this. It's exactly the same thing. So now, I mean, the value is somehow stored already and it's publicly available, as I said before. But here we can also say public to make this thing even easier to access. If you want, you can always access anything on a blockchain, really. But this is just for ease of use. If you make it public, here you're gonna see. Actually, I need to show you the deployment process. So if you go here on this tab, and you can see here the contract compiled. So I have here, I can pick which contract to deploy. So kind of install on the blockchain. And I can just pick this one and I do deploy. As you can see here, I did a fake transaction on a fake blockchain. See, this is like a virtual machine inside Remix. So it's a fake blockchain doing transactions. And here you can see this transaction was sent from this fake address, which has a bunch of fake ether. So you can see even just deploying the contract, so installing it on the blockchain has a cost, which increases, of course, with the size of the contract. Sorry. And here you can see we have a bunch of fake addresses where we can use to simulate purchases of tickets, for example. So let's continue by okay. So we have deployed the contract. So I picked the right contract here, and I click on deploy. And here you can see now I have a deployed contract, and I can interact with it. So making this public, making the price public, what it really allowed me to do was to have a public getter for the value. So I can click here and I'm calling a function, and the function is just giving me its value. So it's creating a getter for it. And one thing that is really, really important to remember is that public does not have the same semantic as in other programming languages. So if I'm making something public, it does not mean it can be modified by anyone. Okay? It just means a public getter is being made for this. For example, if I delete this and I remove public and I make it again, it's private by default. So I don't have it anymore, which does not mean the value is not publicly available. It just means I don't have a convenient getter to access it. Okay? I need to do some more complicated work. Now, I can just do this thing again. So we have public, and yeah, this was a lot of talking for a simple variable, I know. And now we need to store the information of who has the ticket and who doesn't. So how do we do this? Is that we can use another data structure in Solidity, which is called the mapping. Now, the mapping is sort of like a dictionary with the caveat that you cannot iterate over its elements. So in a dictionary, usually you can do keys and then you can iterate over the keys and do things. This is not a thing in Solidity, just because, as I said, there's no use case for this. Everything is built to be like as fast as possible. So a mapping is already a no one access from one key to a value. Sorry. So let's see, how can I make this clear? The mapping is basically associating the user with has a ticket, with the answer to the question has a ticket, okay? So how do we do this? What is a user on the blockchain? As I said before, it's an address, it's a public key. So with an address, you can identify if that user, if that owner of that wallet has a ticket or not. So we can just associate an address, which is going to be the key of the mapping, to a Boolean value. So here, I just say for every user, there's a Boolean which tells me if he has a ticket or not. In the blockchain, since we don't want to waste space, we just assume that all the values are initialized to 0 by default. So now all the addresses existing in the possible range of addresses is just initialized with a false value. So we can give this a name, maybe tickets, just to say we're storing the tickets here, and we make a public getter for it. So here we already have in place, if we deploy a contract, which gives us two pieces of information, the price, which is 30, and the tickets. So who has a ticket and who does not have one. So how do we check this? Is you pick your own address. This could be simplified in a real application, for example, a QR code. And you pick an address. Let's pick this random one here. I copy it, I paste it here. And you can see that it's telling me, hey, this is false. This guy does not have a ticket like anybody else, since we know the contract is not initialized. I'm gonna wait 1 minute, so I'm sure everyone is at the same point and is convinced about what I've said. I can reproduce, and then we're gonna move forward.
You have a question?
Yeah, so
Yeah.
the mapping is basically creating a dictionary, right?
Yes, it's creating precisely just a hash map, so you cannot really iterate over the keys, but it just connects really an address to a value. Yes, but yes, it's a dictionary. Okay, I'm gonna move on. So what is really interesting here, if you want to see this from a Web2 perspective, so a normal server, is that here we already have two endpoints for, let's put on the contract, it's our server. You can already have two endpoints that are publicly available to anyone and that we can use to check, one, the price of the ticket, and two, if anyone has a ticket or not. Okay, this is already like exposed through the public modifier. Now we want to also do operations that change the state of the blockchain, because of course we want to, well, buy tickets, for example. That would be nice. So the first thing we do is that we create a function. We can call it whatever we want. Let's say buy ticket. And yeah, here we need to specify a couple of things. The first one is that it is external. So what external means is that it can be called by anyone. I'm not gonna go through all the modifiers, but yeah, this is like the one that you want to use when you want to have anyone be able to interact with the blockchain. Okay, so anyone can call this endpoint. And what can they do? Well, they need to pay for something. So how do we encode the fact that they're paying? We have another modifier which is called payable. So when you add payable to a function, you're saying I can attach some amount of money to the call of this function. So I'm basically sending money, plus I'm executing the function. And then here, what I need to do, the most important thing is I need to update my mapping. So we just go to the mapping and we say, hey, tickets. And here, what is really important is that like in the function context, we have a couple of things that are useful. We can access the amount of money sent with a message value, and we can access the sender, so the user, with a message.sender. Okay, this works as long as you're inside that function. So here we can just say, hey, I want to change the key of the sender to be true for the mapping. Sorry, Python habits. So yeah. So here what I'm doing is I'm modifying the mapping. I'm modifying the mapping for the key represented by the address of the sender. So the person who actually called the function, because it's the one that is willing to buy the ticket, and I'm putting it to true. Now, if I were to just leave the function like this, well, it would not be very useful, because anyone can call this and anyone can just say, yeah, I just got a ticket, you know? So the first thing we need to correct is the only thing we need to correct is that we need to make people pay for the ticket. So how can we make sure we're paying for the ticket? We can just apply a condition on the value sent. So if the value that we send, so if message.value is not equal to the price, then I'm sorry, but we need to revert the execution. And we also give a nice error message like wrong amount. This alone has already created a system where the contract is receiving the money. And of course, we can expand this as much as we want. I'm gonna do some more expansion or like some key features, but we also need a way to withdraw the money from the contract to the actual user that needs to then use them to run the festival, you know, and things like this. But already like this, we have something somehow functional. So let's try this. Let's try to deploy this. Is everything clear so far? Everyone has been able to follow up to here? Okay.
I have a question.
So
Actually,
yes.
there's a like in this case, because you said every computation you have to pay. So if someone just keeps pinging this, and they have the wrong amount, who would pay for all these reverts?
To give you a simple answer, what usually happens nowadays is that the transaction is first simulated. Well, the user would pay for it. So if you send the wrong amount, you just pay for the wasted computation that you did, which was useless, but nodes still had to do it. This is like a DDoS attack protection. But this usually does not happen anymore, just because what we do is that we simulate on the browser if the transaction is gonna execute or not. It's gonna work or not, and if it doesn't, we don't even let you send the transaction. So from a UX point of view, you never really get to the point where you send the wrong amount. This is usually impossible. Actually, the browser would even already set the correct amount for you. So it's really hard to make a mistake. This is more like on the low level, and then the browser is making the hard work to make this nice.
Great, thanks.
Okay. So moving on, we're gonna try this contract out. So what you can do is that we can delete the contract we had before, and then what we do is that we deploy the new one. So it compiled, as you can see. We can just deploy again. Transaction to deploy. I paid some gas, and I here have a new contract, and this contract has the two getter functions we had before, but it has a red function because it's changing the state of the contract, which allows us to buy a ticket. So I can already try to interact with it without specifying the amount. And if I do this, you're gonna see, yes, we have an error here, and it says, yeah, the transaction has been reverted to the initial state. The reason is it's the wrong amount, so everything went as we expected. And how do we actually add value to this? We can specify here a value in way. So we just say 30, and it should work now. So if we try to buy a ticket now, we're also touching the amount required. And see, the transaction went through. And most importantly, if I take my address, so I copy paste from here the address I used to do the transaction, I go back here, I paste the address, and I try to get tickets. I obtain true because I actually have a ticket. So this is just how simple it is to check if someone has a ticket or not from a backend perspective. This is really that simple. Of course.
Question?
Yes.
What did you do before click on buy ticket again that it was successful? So where did you specify the money?
Oh yeah, sorry. It's a bit unintuitive, honestly. This is very bad UX, but here you have a value menu. Value
so it should be more than 0 for it to work. And it should be 30.
Yeah. So did everyone manage to reproduce?
Yeah, should be good.
Okay. So, okay, so we already got so far. Honestly, like if you were to stop here, we would already have like a functional ticketing system. The money would be lost because we have no function to withdraw the money. But it would work, you know, you could check if someone actually spent some money to obtain a ticket. We could make this fancier. Of course, I could introduce NFTs here and make the ticket an NFT, which would be like not that different. Here, we would just call a function to create an NFT. But we're not gonna do this today because it's a bit too much. What I really want to show you, which I think is more interesting, is let me see where we are at. Yeah, like for example, let's see how it works if we want to have some additional admin controls on the tickets. So for example, let's say we want to change the price. As I said before, here the price is a variable, and even though it's called public, this does not mean we can change its price. It just means we have a public getter for it. So how do we actually change the price? By default, we can't. So if you were to just put this like thing on the market like this, nobody could change the price, which is something that could be desirable. You know, at some point you might want some things to be, if you really want to be sure that one thing cannot be changed, that it's immutable, this is a very nice thing to have. It's by default, you know, it's very powerful, and you cannot really undo things. You know, you cannot delete things on the blockchain. If this is immutable, this is really immutable, which is, I think, nice. But in, of course, the real world, where people make mistake, we want to be able to update stuff, or maybe even over time. So what I'm gonna do is I'm gonna make a function which is called setPrice, which works basically like a setter in object-oriented programming. And of course, we could make this nicer. You know, we could make this change the price over time. For example, like instead of having someone to change it manually, we could just say, hey, after the third week of the selling, after 3 weeks of selling, just increase the price. And it doesn't have to be discrete, it could be linear, you know, over time, increase it every second that passes, increase it by 1 cent. You know, you can do all sorts of things, but let's keep it simple. It's just to give you an idea of how powerful this thing is. And yeah, so if you make a function set price, we need to make it external because we need to have people be able to call it. But there's a big flaw here. We cannot allow everyone to call this function, otherwise we have a small problem. So what we can do here is that we can protect the function. How do we protect this function from being called from someone else that is not allowed to? We can do something very simple. We can just create an owner of the contract. So we can just create another variable here. We just say, hey, it's an address, public, why not? That contains the information of who is the owner. And then we need to set it somehow. In the easiest case, we can just hard code it, but of course this can be set dynamically. So for simplicity here, I'm just gonna do this. So yep, I just copy paste my address. So you go here and you can copy paste it and it should work. So only when I'm gonna send with this account and not the others, I will be able to change the price. So we still need to write the body of the function. So we just write that simple condition. It literally says if message sender is the owner, then now if it's not the owner, then we just revert the condition. So we revert and say unauthorized. And there you go. And we need one more thing. What is the wording about? Okay, yeah, this is normal. And then we can just say, hey, price equal. And here we can just set an argument for the function like you would normally do in normal programming. New price. And then what we do here is that we say new price is the new value for price. I guess this is not rocket science. If you're here, you should all be familiar with this. This is just a setter with an additional condition. And now we can test this out. So if I didn't miss anything, this should be fine. So we just go here and we can delete the previous instance of the contract. I deploy the new contract And here I'm actually gonna do the opposite first. So I'll try to change the price. But let's try to change the price with someone that should not be able to change the price. So let's pick another address like this one. And let's try to set the price to 15. See the transaction here reverted. So we can see the error is unauthorized. And now if we try to change the price with the actual owner, we can see that the transaction should pass. So here I do, for example, let's say 45. I think this should be the actual price of Balélec tickets. You see it passed. And now if I get the value for the price, it's 45. It's not 30 anymore. And I can, of course, buy a ticket and do whatever I want. But in fun fact, this little thing here that you saw here, it's one of the most common things we forget in smart contract development. And it's one of the most dangerous and painful things you can forget. Because when an admin function is exposed, as I said before, contracts are immutable. So you cannot change them, once they're deployed. You can with some big caveats, but usually you just cannot. So if you forgot this thing and you have actual money inside it, and for example, it's a withdrawal function to like withdraw the money from the contract, then you have a big problem, and we pay auditing companies thousands and thousands and thousands of dollars just to check for stuff like this among serious vulnerabilities. But this is like, as stupid as it may sound, like companies do forget this stuff. So yeah, we can even make this a bit nicer. I'm gonna be a bit faster in this, maybe. No, it's fine. It's fine. We have some time. So yeah, is everything clear so far? Good. So what we can do is that we can make this a bit nicer. When I set some sprinkles of Python, you might be asking yourself, like, where is Python and all this stuff we have seen so far? And one thing I like about Solidity is that they made quite nicely is that they have one additional thing that is called modifiers. And modifiers are a way to make the code more readable, even though some might argue that it's not necessarily more readable, but it's just normally used in the industry, so I'm going to show it anyway. So imagine you have a bunch of admin functions, and we want all of them to be protected with this condition. Instead of copy pasting this every single time or making like helper functions, we can make a modifier, which we can call only owner. And what this modifier does is that it just does the check we want them to do. And then it executes the rest of the function. So this is a special syntax, and it says, okay, it's just gonna inline this at the beginning of the execution, and then it's gonna execute the body of the function. So here, if I add the only owner modifier, what is gonna happen is that the body of this function is gonna be actually this, and only after this. Okay, this is nice. This looks a bit Pythonic, sort of, and it's actually good as long as you don't forget to put only owner. Yeah, that should be it. And so let's try. Let's see if this works. We should just verify that the behavior stays unchanged. So we deploy. We have a new instance of the contract, which should be functionally equivalent. We set the price to 15. We try to call with the wrong address. So I pick the second one, for example. It reverts, it says unauthorized. And then if I do the same thing again, but with the first one, I can just, yeah, say here, whatever, I can lower the price, yes, and it works. Okay, so this is nice. Depending on how much time I have left, I could show some even nicer details, for example. They could improve the content readability, or we could even stop here or discuss if there's Q&A, for example. But the point here, what I really want to show you is that like in literally 30 lines of code, we have a secure system to like manage prices, and everything is simple yet powerful because it's secure by default, it's convenient. And yeah, hope one day, like at least for like things that handle actually the financial part, this stuff should be handled by the blockchain because it does it really well. You don't need to spin up your own blockchain. You can just use blockchains like Ethereum, which are very powerful, support the scripting languages, and you can just use them to build your own use case. Not everything needs to be on the blockchain, but like for things that have a value, or when you're handling like the financial part, I think it's very important. And yeah, that's pretty much it. I think this is like the beauty of like Solidity and smart contracts in general. Questions? Okay, cool. How much time do we have left? Oh, sorry.
It's not, I don't know if you're trying to explain this now, but you mentioned there are some caveats where you can actually yank a contract. Can you maybe elaborate on that?
Oh, to update the contract, you said?
To change or remove a contract?
Yeah, okay. Okay, so and this is more like niche, but I'll answer it again. I'll answer it anyway, I guess, even though it might be overcomplicated. In the past, we had a feature which is called self-destroy, which allowed a contract to be removed from existence, which does not mean you can. It just prevents people from calling it again, but you cannot just delete the contract. The state will be there. The history of the contract will be there. So you cannot just undo what if you have done something wrong. You're just making the contract inaccessible anymore. This code, however, was very dangerous, so it was removed recently. Another option that you have is that, to give you an idea, we have patterns to make upgradable contracts. So what you can do is you basically have a contract which stores all the information, and then that contract has a pointer to another contract that you can change that pointer, if that makes sense. So this is how it works, but it's often very messy. It's like you always have like two schools about this. Some people just don't want to use it. I don't. Like, I've been working in the industry for 3 years. I have a full-time job now at Curve Finance, for example, which is like in a top 10 protocol. We don't do upgradable contracts. We handle millions, but we would rather afford the mistake of like afford the price of the mistake. We can afford the price of the mistake, but like, for example, smaller protocols, they cannot do that. So if they do a mistake, they're dead. And in those cases, for example, those protocols usually go for proxies, but it's not necessarily additional security. It's just sometimes you can fix things by adding new functions, but it's most of the times like very dangerous. Like, for example, to give you an idea, if you're using a proxy and in the new version of the code, you invert the order of those variables, you've broken the code completely. Like, it's so dangerous, and it's not ideal, just because blockchains are not meant for upgradability. And there is some discussion in the community around whether we should make them upgradable or not. But I think if you design your contracts correctly, you don't need upgradability. What I'm trying to say is you can always make your contracts modular. So for example, this could be only one piece, and then you make sure it's connected to another piece that you can eventually replace if you really need to. It's hard to understand when you have such a basic example, but a good architecture, it's often better than upgradability. And this is like my personal take, but I'm against it, because I also think, like, what's the point of having smart contracts if one person can change them at any point in time? It's you're losing the trust of seeing what's the code and saying, okay, I'm trusting this code and not this person. So
just another small question.
Mhm.
Are there competing implementations of the EVM, or is everybody pretty much running the same code?
Before, it used to be all EVMs used to be very, very similar with each other. Then you have a couple of things that deviate between each other. Like now it's messy. Now it's messy because you even have a website where you can compare like every single EVM, which things are supported and which are not. So yes, this is something you have to take into account. But usually,
I don't mean
Sorry?
on separate blockchain. I don't mean on separate blockchains. I mean like on the Ethereum blockchain. Is everybody running literally the code, or do people like?
Yes. No. Okay. Sorry. Okay. In this case, okay. So on Ethereum, you have multiple implementations of the same Ethereum client for security reason, because if there's a bug in one, then you cannot
Exactly.
really afford to have that bug everywhere. So we just have multiple implementations in different languages for security reasons. This said, while there might be uncached differences, we suppose all clients running on the same blockchains are fully EVM equivalent.
That was my
This is a,
question.
yeah, yeah, it's an assumption we do. It could not be the case, but this is usually well tested. And we, yeah, this is very well tested. Like this is, if you mess this up, honestly, it's. But even if it was the case, yeah, even if it was the case, let's say we have one client which is as a different version. If the different version leads to a different behavior, the blockchain would handle this because they would, in the consensus part of the blockchain, they would see one node is proposing a different output. So they would be like, hey, there's something wrong going here. Then I'm not sure about how this would be resolved, but this would not be uncached.
Yep. Thanks.
No worries. So any other
I have a quick
questions? Yes.
When it comes to the state of the smart contract, is there a price to pay based on like the resources that consumes? I assume that. Okay.
I cannot hear it anymore. I'm sorry.
Well, that was the question.
Oh, okay, sorry.
Yeah. And how does
so
that calculate? Who pays
okay,
for that?
that's a very interesting question, and I love to answer it. So if you go here, when you compile the Solidity code, you end up having a list of opcodes that you can see here. This is like 0001, every single one as a number. So I think I can even show you here. Let me see. We usually don't debug. No, we usually don't do this stuff here because it's Remix is more like for presentations and beginners. But here you can see like I'm debugging the thing, and you can see all the opcodes that I'm executing. I'm sorry, my voice is dying. And here you can see every single opcode has its own cost. How do you know how much everything costs? It's here. So let's pick, for example, the addition of operation. You can see we have a minimum gas cost of 3. And I think this one is always free all the time, as long as you do an addition. And for example, you have other operations. Like multiplication is supposed to be more complicated, so it costs more. And in the end, how you compute the cost is just you go through all the opcodes that we went through and just do the sum. And then this is the part that contributes to the actual computational cost. And then you multiply this by the state of the network. So we have that coefficient that depends on like how congested the network is here. And you just multiply that sum by this coefficient. So this is basically how the cost is determined. And then the cost, of course, it's in Ether. So it might also oscillate depending on the price. Now, one thing I wanted to say is, how do we actually decide, like, how do they pick this cost? You know, like, did they just pick numbers depending, say, hey, maybe multiplication is harder than addition, so let's make it more expensive? No, this is very well thought. The idea was to replicate the consumption of an actual machine. So, for example, they did some benchmarks, and they estimated like the times it takes in milliseconds for an instruction to execute on a processor, and they try to keep it as close as possible to the actual cost of a processor, and to emulate even further like how close this resembles to the cost of a processor. For example, when you're accessing storage, so the data on the blockchain, they have created an artificial cache, which makes things more expensive the first time you access it. And then it's cheaper once you have accessed it already, because you already have the value in the cache. And how they do this, it's very simple. Like, for example, let's pick a code that access memory. Like, for example, an S store here, this one stores into memory, into storage. And what we do here is that you can see the cost by default is 100, but if it's your first access, so if the state of the key is called, you can see it's more expensive. And they did all this stuff to emulate as much as possible what would be the expenses of a real computer, so that like we don't have to make weird algorithms just because one thing is cheaper than in real computers, you know. So this was the idea. Is that clear?
Yeah, so basically, for example, when you were adding an address to the map, the act of actually storing this information on the blockchain is included in the, let's say, in the execution.
Exactly. Like some opcodes have dynamic costs depending on what the size of the input. I think, for example, an store here, which should be what we use for the mapping. Like I think if you make it bigger, like if you're setting a value to 0, since you're cleaning the state of the network, it's only 100. But if you're putting an actual value, it's like 2,000, and then it's even more expensive if it's cold. And if the current state of the value was something different, it changes the cost. It basically, like, everything is taken into account in the way opcodes are defined.
Thank you.
No worries.
All right, Alberto,
So-
how much time do you think you have left for going through the code?
I'm good. I could go even further but honestly, I feel like it's okay like this. Like, yeah, unless people want to continue.
Because anyway, you'll share the full code in case you miss something later on, so we'll share it in the follow-up, the workshop. But yeah, maybe
Yeah,
you
I
can close
missed.
up and then we'll switch to the quiz. How about that?
Oh yeah, sure. So okay, I'll try to. Yeah, okay, we can do one last thing real fast. I'll try to copy paste so that we can go faster. So imagine that you want to reuse this contract every time, and maybe from 1 year to the other, like the owner of the contract changes because it's not the same admin that is handling the contract anymore. We can make this more like scalable. And for example, what we can do is that we can use a constructor. So if you're familiar with this, it's basically the same thing as you would do in Java. So every time you deploy a contract, you get the constructor. I'm just gonna copy paste this for speed because I'm very excited to see how the quiz goes. So here you can see we can just initialize the owner at construction. So every time you deploy a new contract, you have a different owner. So can even remove this. And then what we can do is we just, yeah, it's that simple. And now when I try to deploy the contract, it's gonna ask me who is the owner before I can deploy. Okay, so here it can be me again. So I go here and I paste it and I deploy and I create a contract with me as the owner, but it could also be someone else. Those things are totally possible. Okay, so this is the old contract. Let's deploy again. So I'm sure I know which one I have. See here, if I try to change the price to something else, I can because I am the owner. And if I'm someone else, it doesn't work. So this is how you make things more scalable. For example, if you have multiple instances of the same contract, like imagine you have a really good template for tickets. You don't want to use it only for Balélec. You want to use it for any kind of like event, you know, and this is how you can do it. So here, if I change the owner to someone that is not the actual owner, well, we have an error and it reverts. So this is what I wanted to say. I shouldn't be missing anything else. Yeah, I think we can go with the quiz, and thanks for listening.
Cool, let's give a round of applause.